Hey calculus, we are going to learn the derivatives of e to the x, ln x, and any exponential function. An exponential function, remember, is where x, the variable, is in the exponent. And then we're going to practice using these three new derivatives in the chain rule. So right up here, the derivative of e to the x, right here, the derivative of e to the x is itself. All right, it is the only function that is its own derivative. Alrighty, so let's look at example number 1. E to the cosine of x. This is an exponential function because your variable x is in the exponent. Whenever you have an exponential function, the base will always be your outer function. So our base here is e. So we write the outer function as e to something. All right, so our outer function is e. Our inner function is cosine of x. All right, remember, if you have an exponential function, anytime x is up here in the exponent, the base will always be the outside function. So let's take the derivative of the outer function. First step in the chain rule. The derivative of e to something is itself. It is e to something. All right, so this whole gig here is the derivative of the outside function. The inner as is, we plug in right here. So we plug in our cosine of x right up there. Cosine of x goes in the exponent. The third step, so that, if we label our parts, is the inner function as is. All right, now the third step of the chain rule, we multiply everything by the derivative of the inner. And we know that the derivative of the cosine is negative sine of x. Now, I would put that in parentheses so it doesn't look like subtraction. But this right here is our third step, the derivative of the inside function. Okay, to simplify this, remember the numbers go out front, so we've got a -1 here. So I would write this as negative sine of x times e to the cosine of x. There you go, final, best, full credit answer. The next part of this note sheet, we are just going to review the log properties. Logs are kind of weird and you haven't probably seen them for a while. So the first one, the log of a power. The log of a power tells us that we can take that exponent right up here and we can move it to the front. So that would be the same as the exponent d times what's left, or what is there, log base b of c. Log of a power. The second one, the log of a product. The operation that goes with product, you guys, is addition. Remember, product is multiplication. So we can expand this c times d with addition. We just put this log base b in front. So it looks like this. The log base b of c times d is equal to log base b of c, the first factor, plus log base b of d, the second factor. We expand multiplication with addition. We just put that log in front of each. All right, and the third one is the log of a quotient. That's division. The operation that goes with division in the math world is subtraction. All right, so we can expand this fraction right here with subtraction. We just put log base b in front of the numerator. So we have log base b of our numerator c, and then minus log base b of our denominator d. All right, so those are the properties. The next thing that we're going to learn is the derivative of ln x, right here. ln x. The derivative of ln x is 1 over x. So it brings a fraction into play. So let's look at example number 2. Our function is 4 times ln, the natural log of 3x. We are natural logging 3x. So ln is my outer function. So remember, bring the number along in front, the coefficient. So my outer function is 4ln. And then my inner function is 3x, because I am taking the natural log of 3x. So when we take the derivative, the 4 comes along for the ride. I'm going to make it a fraction. Make everything a fraction when ln is your outer function, because you're going to have fractions. The first step of the chain rule is the derivative of my outside function. And we just learned that the derivative of ln is 1 over x. So when we write our outer function, since we need a blank set of parentheses, we write 1 over x like this, 1 over something. All right? So this whole thing here, that is the derivative of the outside function. All right? That's the first step of the chain rule. The derivative of ln is 1 over something instead of 1 over x. Now we plug in our inner as is inside that blank set of parentheses. So 3x goes right there. All right, so I'm just going to make a little note there. That is my inner as is. All right, finally, I multiply everything by the derivative of the inner. The derivative of 3x using the power rule is 3, and I make everything a fraction. So this is my derivative of the inner. All right, now to simplify this, remember to multiply fractions, we multiply the tops and we multiply the bottoms. So on top, we have 4 times 1 times 3. That gives us a 12 out front. On the bottom, we have 3x times 1 times 1. So that gives us 3x. All right, now when we simplify that, we take the 12 divided by 3, and that gives us a 4. The 4 is still in the numerator. All right, in fact, I'm going to write it like this. I'm going to really slow it down. It becomes 4 over 1x. And then when we simplify that, we get 4 over x. And that is my final best answer. I could also write that as 4x to the negative 1. Either one of those is acceptable. So those are my final answers, possibilities. All right, a little bit tricky. Just go slow. Let's look at example number 3. Here our function, we're taking the natural log of x to the third. So our outer function is ln, and my inner function is x to the third. All right, so the derivative of the outer, the derivative of ln x is 1 over x, but we write it as 1 over something. Whenever ln is your outer function, you write the derivative as 1 over something instead of 1 over x, because we need somewhere to plug the inner as is in. So this right here, that whole thing, that is the derivative of the outside function. Second step of the chain rule, we plug the inner as is right inside that blank set of parentheses. So that is x to the third. That is my inner as is right there. All right, the third step, we multiply everything by the derivative of the inner. The derivative of x to the third using the power rule is 3x squared, and make everything a fraction. Put that over 1. So that is the derivative of the inner. There you have it, all 3 steps. To simplify this, we simply multiply the tops and we multiply the bottoms. On top, we just have 1 times 3x squared. On the bottom, we just have x to the third times 1. All right, now when we simplify this, that looks like this. We still have 3 in the numerator, but we have an extra x in the denominator. We could also write that as 3x to the negative 1. So that is your final, best, full credit answer. Either one of those choices will work. They are both equivalent. Okay, I just realized that we forgot to review log functions up here. So rather than start the video over, we're just going to jump back up there. Sorry about that. We just want to review going back and forth between log form and exponential form. So here we go. Remember, logs right here, logarithmic functions, they isolate exponents. All right, they isolate the exponent on one side of the equation. All right, so if we look at number 1, our exponent is x. So when we put that into log form, that exponent x is all by itself on one side of the equation. All right, then we need the word log. Our base is 5. The base is kind of easy to pick out. So the base we write right here below. And then what's left? 70. So that goes right here. So 5 to the x is equal to 70. I can put that in log form. That exponent x is equal to log base 5 of 70. Let's look at number 2. If we put this in exponential form, or excuse me, if we put this in log form, that exponent x is all by itself on one side of the equation. We need the word log. Our base is e, so we write that below here. What's left? 17. That goes on the end. So e to the x is equal to 17. We can put that in log form. X is equal to log base e of 17. Now, I'm going to highlight this. This is kind of a fun little abbreviation. Log base e in the math world is equal to the natural log, ln. All right, it probably should be NL, but someone way back in the math world decided it was LN. So LN simply means log base E. All right, so I can rewrite this as x is equal to ln 17. All right, this log base E is the same as ln. Alrighty? All right, and then finally, this whole thing right here, if we break apart everything, hey, that b represents the base. Alrighty? A, right out here, that represents the exponent. It's all by itself here. So a is the exponent. And what does c represent? Well, c is the answer to b to the a. All right? The next thing that we want to review are the fact that ln x and e to the x are inverses of each other. So let's try to prove that. Let's take this right here and put it into exponential form. All right, so to put that in exponential form, we start at the base, e. We swing out and get our exponent. Remember, our exponent is always all by itself. E to the y is equal to x. X is what's ever left. All right, now I want you to look at these two things, e to the x and this form of log base e to the x. You can see there that the x and y's are switched. The x and y's are switched. That is a key relationship between a function and its inverse. So it's just kind of a way to prove that log base e and e to the x, those are inverses. They undo each other. So that's what it says right here. If the function is ln x, the inverse function is e to the x. This is the symbol for inverse right here. In fact, let's circle that. This right here, that is a symbol for the inverse function. Alrighty? And then the second row, if the function is e to the x, the inverse function is ln x. And that should be an equals right there. My apologies. All right, so the reason that helps us is look at these examples. If you see ln and e right next to each other, they undo each other. That's what inverses do. They cancel each other out. So if we were to simplify that, we get y is equal to x. That's what's left up here. This is much easier to take the derivative of. This up here would be a chain rule, but this, we know the derivative of x is just 1. All right? Same thing over here. If you see something like this, e to the ln x. E and ln are right next to each other. They cancel each other out. If you simplify this one, it's y is equal to x, because that's what's left up here. And now if we take the derivative of x is 1. So the reason it's helpful to go back and review those inverses of each other is it makes derivatives a lot easier. So be on the lookout for e and ln x right next to each other. All right, the final part of our note sheet is to find the derivative of an exponential function of any base. We kind of represent it as b to the x, any base. Remember, an exponential function is any function that has x, the variable, in the exponent. So the derivative just looks like this. We rewrite the function again, and we multiply it by the natural log of the base. That's the formula that you have to follow. So it's pretty simple. Let's look at these examples. If we want to find the derivative of 2 to the x, exponential function base 2, we rewrite the function 2 to the x, and we multiply it by the natural log of the base. All right, so the derivative of 2 to the x is 2 to the x ln 2. If we apply that formula to exponential function base 3, 3 to the x, to take that derivative, we rewrite the function 3 to the x, and we multiply it by the natural log of the base. Easy peasy. The derivative of 3 to the x is 3 to the x times ln 3. If we take the derivative of 13 to the x, that's an exponential function base 13, we follow the formula. We rewrite the function as is, 13 to the x, and we multiply it by the natural log of the base 13. And finally, example number 4. What is the derivative of 100 times 1.07 to the x? Well, that 100 comes along for the ride. Remember, coefficients come along for the ride. And we use the formula for 1.07 to the x. That's exponential function base 1.07. So we rewrite the function 1.07 to the x, and we multiply it by the natural log of the base 1.07. I would put this in parentheses because that x only applies to the base. It doesn't apply to 100. So the derivative of an exponential function of any base, let's review, b to the x. The derivative is you write the function again and you multiply it by the natural log of the base. Finally, that last example, what if we had to take the derivative of a function that looked like this? Y is equal to 2 to the 3x. This is a composite function. All right, we have two functions going on here. We have exponential function base 2, and we have the linear function 3x. All right, whenever you have an exponential function, the base is always the outer function. So this is base 2. So our outer function is 2 to something. And my inner function is 3x. All right? So if we take the derivative of that, well, the derivative of the outer. What's the derivative of 2 to something? Well, we follow this formula up here. The derivative of 2 to something is 2 to something times ln 2. This is the derivative of the outer. We're just following this formula. So the derivative of 2 to the x is 2 to the x ln 2. The derivative of 2 to something is 2 to something ln 2. And we write it like this because we need somewhere to plug in the inner as is. So we plug the inner as is right up in that exponent. So 3x goes right there. That is the inner as is. All right, and finally, don't forget the last step of the chain rule. We multiply everything by the derivative of the inner. The derivative of 3x is simply 3. So that is the derivative of the inner. All right, to simplify this guy, that number has to go out front. So we need 3 times 2 to the 3x ln 2. Final best full credit answer. Make sure you get parentheses here because that exponent 3x only applies to base 2. It does not apply to 3. Oops, don't forget y prime, the right symbol for derivative. Thanks, calculus.